And work is defined as the change in energy. Now, the conservation of energy, like energy is always going to be like it's not going to be destroyed, it's not going to be lost. It just only can be transferred. And what work does is that it's basically an external force over some displacement. And remember, this force has to be parallel to displacement. So we can define it as the cosine of an angle. So basically, and work is a vector as well. So it can mean it, unlike energy, it's positive or negative. If it's positive, then you're gaining energy. But if it's negative, you're losing energy. So and basically what work does is it just transfers all the energy to like something else like thermal energy or like energy for sound and all that stuff. So with this definition, we can actually use um, this in conservation of energy problems. But first, I'd like to show you like where it comes from. So let's refer back to the Newton's second law. F equals ma, or sigma F. We're talking about the net force. So we can redefine acceleration as dv over dt. And this is how we get like impulse and all that stuff. But we're not looking for impulse, we're looking for work. So what I can actually do is use the chain rule to split this into dv over dx and times dx over dt, because it's the same thing, it's just the dx's cancel out. And this is true because of the chain rule, because when you have two like composite functions, basically you take the derivative of the outside and then the inside. So what I mean by that is, so m dv over dx and then times dx over dt. And you see here that these will just cancel out, and it's the same thing as dv over dt, which is acceleration. But we know from kinematics that dx over dt is actually velocity. So we can rewrite this as m f equals dv over dx times velocity. And then we can multiply dx on both sides, so we get sigma f dx equals mass times velocity times dv. Now you can recognize this as, momentum. And that's basically what that is. So now we're going to integrate both sides. And we basically get like, and since work is a force over some sort of displacement, that is our definition of work in terms of calculus. So it'd just be f times the integral of f with respect to x. So using this formula, we could just sub that in to get integral of mv V, or momentum dV, and using the reverse power rule, and since it's with V, you treat M as a constant. So don't add like another V anywhere. Just focus on V. So we basically add 1 to the power and divide by that same power. So work, or the net work to be more specific because we're talking about the net force, is, and also these have to have bounds. So like say x1 and x2, x1 and x2 and x1. So the net work is 1/2 mv squared evaluated at x1 to x2. And you might recognize this as kinetic energy. So basically, what we have derived is that work, or the net work, to be more specific, is the same thing as the change in kinetic energy. So this is actually pretty useful. We can actually apply this to several problems. What we have here is a practice problem. So this is kind of a warm-up question. It doesn't require any of the definition that we've derived earlier with work. It's just like an energy problem. So a biker approaches a hill at 8.4 meters per second, and the combined mass of the bike and the rider is 100 kilograms. So what you're supposed to do is find the kinetic energy of the system and what height the biker will come to rest. So using the formula, kinetic energy equals 1/2 mv squared, we can find the kinetic energy of the system. So we can just plug that in. So then we'll get an answer of 3,528 joules. So using this, we can actually find the height in which the biker has come to rest. So that's basically when all the kinetic energy is transferred to gravitational potential energy. So you'll be at the maximum height possible, but you won't be moving. So at this point, the kinetic energy will equal the potential energy. So that would be equal to mgh. So then we do 3, 5, 2, 8 equals 100 times 9.8 times h. Which should gives you an answer of 3.6 meters. So if you're curious, there is work being done, but it's not from like friction or anything like that, like stuff that makes you lose energy. Um, like the more distance you travel. Um, so this will be brought up later, but it it's the work done is by gravity because like say if you're on a hill, right? You're gonna keep going up and up and up, but you're gonna be slowing down. So it's gravity that's acting upon it in the other direction, making you lose kinetic energy, but at the same time gaining potential energy because your height is increasing.